As we have seen, in order to construct field extensions, we need irreducible polynomials. In this lecture, I'm going to explain to you Gauss's lemma, which helps us understand when some polynomials are irreducible. The statement is the following. So this theorem is called Gauss's lemma. It says that if f is a polynomial with coefficients in the integers, so this z square brackets t means we're looking at polynomials in the variable t whose coefficients are all integers. And suppose the content of f is 1. So I need to explain to you what the content of f means. So if we have a polynomial equals a naught plus a1t, so polynomial in the variable t plus an t to the n, then the content of f denoted cf is defined by cf is just the GCD of the numbers a0, a1, an. So if the content of a polynomial is 1, it means that the GCD of its coefficients is 1. So if you have a polynomial with content 1 and we write ft as a factorization ut times vt in qt. So I'm not claiming that ut and vt have integer coefficients. I'm just saying that ut and vt are polynomials with rational coefficients. Okay. Then there exist rational numbers a and b such that ft is equal to aut bvt, where these scalings of the polynomials have integer coefficients. aut bvt belong to zt. Okay, so basically what it's saying is that if you have a factorization in qt, then you also have a factorization in zt. And the proof of this lemma, this theorem rather, Gauss's lemma, is another lemma which is also due to Gauss, which says that content is multiplicative. So the proof uses the following lemma. This is also due to Gauss. For ut vt in zt, the content of u times the content of v is equal to the content of u. So the content of the product of two polynomials is the product of their contents. Now to prove this lemma here, we can assume that the content of u and v is 1, because if the content of u is not 1 or the content of v is not 1, then we can divide u by its content and get a polynomial with content 1. Similarly, we can divide v by its content and get a polynomial with content 1. So we can assume that without loss of generality, and then we need to show that the content of uv is also equal to 1. For this, we will use a technique that is very useful for analyzing polynomials, which is the reduction of coefficients modulo a prime. Now, we need to show that the content of uv is 1, for which it is enough to show that no prime divides all the coefficients of uv. Right? So we'll use reduction modulo p. So let me just explain that. So the idea is reduction modulo p. So if you have a polynomial ft equals a0 plus a1t plus an t to the n with integer coefficients, then you can take each of these coefficients and reduce it modulo p. So define f bar t to be a0 bar plus a1 bar t plus an bar t to the n, where ai bar is the image of ai in z mod pz. Okay, so this is a polynomial in z mod pz. Now this reduction map has a very nice property that if I take f g bar t, then this is f bar g bar t. So this reduction map is a ring homomorphism. Now to say that a polynomial is primitive, it's enough to show that for every prime p, its reduction modulo p is non-zero, because that would mean that the prime p does not divide all of its coefficients. So the observation is f t belong to zt is primitive, i.e. it has content 1 if and only if its reduction mod p is non-zero for every prime p. So now coming back to this, we want to show that if, so let's just put this definition down, f is primitive if cf is 1. That's just the definition of primitivity. And so what we want to show is that the product of two primitive polynomials is primitive. And so we take the product and we want to show that its reduction modulo any prime is non-zero. So suppose that there was a prime p with respect to which its reduction was 0. So suppose p is a prime such that the reduction of uv mod p is 0. But then note that uv bar, the reduction of uv mod p, is u bar v bar, which implies that either u bar is 0 or v bar is 0, just because the ring z mod pzt is an integral domain. But this cannot happen because we know that u and v are also primitive. Okay, so this concludes the proof of this lemma here, that the product of two primitive polynomials is again primitive. Now we are ready to prove Gauss's lemma, the main theorem of this lecture. Okay, so suppose we have fx equals ft equals ut vt, where ft is in, as per hypothesis, has integer coefficients, ut vt have rational coefficients. Okay, now if you have a polynomial with rational coefficients, you can clear out the denominators of all its coefficients and get a polynomial with integer coefficients. Okay, say you multiply all the coefficients by some integer n and you get all integer coefficients. You can choose this carefully enough so that the resulting polynomial is primitive. So just take, for example, the LCM of all the denominators, and that should do the trick. So there exist rational numbers a and b in Q such that AUT equals AUT belongs to ZT and content of AUT is 1, that is, it is primitive. BVT belongs to ZT and content of BVT is equal to 1. And we have FT equals AUT. So here we would have AB times FT is AUT BVT. But recall that in Gauss's lemma, we assume that f itself is primitive. Okay, that C of f is 1. And so C of f is 1, then C of AB times f is going to be AB. But here on the right hand side, we have a product of two primitive polynomials. So AB times f should also be a primitive polynomial, which implies that AB is equal to 1. And so we have that FT is equal to AUT times BVT as needed. So this concludes the proof of Gauss's lemma. When we talk about field extensions, we are often dealing with monic polynomials. For example, when you construct the irreducible polynomial of an algebraic element, you can scale it so that it becomes monic. And so if we just talk about monic polynomials, then Gauss's lemma takes a nice monic polynomials with integer coefficients are obviously primitive because the leading coefficient is 1. So here's a corollary of Gauss's lemma. If Ft belongs to Zt is monic and we write Ft equals ut times vt, where ut and vt belong to qt are also monic, then ut and vt are in zt. And the proof is very simple, just apply Gauss's lemma. So what we have is that Ft is AUT times BVT, where AB are rational numbers, AUT, BVT are primitive. Okay, but AUT, BVT belongs to ZT, and if their product is monic, then their leading terms must be equal to 1. The leading term of AUT and BVT must be equal to 1. So this implies that A and B are integers. So what we have is that this implies that A times, well, we know that A times B is 1, so this implies that A equals B equals 1. Okay, so let's look at an example. A very interesting example of an algebraic integer is the nth root of unity. Define zeta n to be e to the 2 pi I by n. This is a complex number. And then zeta n satisfies the polynomial. It's an nth root of unity. So it's a root of t to the n minus 1. Okay, so zeta n is an algebraic polynomial. We can construct the evaluation map, substitution map qt to c obtained by taking t to zeta n. And the kernel of phi t phi zeta n, let's say that is, let's call that phi n of capital phi, it's usually denoted as capital phi n of t. We can assume that this is monic by scaling it. So let's say this is monic and it is irreducible. This is called the nth cyclotomic polynomial. So now phi n is a factor of t to the n minus 1. T to the n minus 1 is a primitive monic polynomial, and so what we have is phi nt is a polynomial with integer coefficients. We can compute some examples of phi nt for small cases by hand. So for example, let's write down n and phi nt for some small example. So if n is equal to 2, then we are looking at zeta 2, which is a square root of 1, which is minus 1. So we just get t plus 1. Minus 1 satisfies the irreducible polynomial, is a root of the irreducible polynomial t plus 1. If n equals 3, then we are looking at cube roots of unity. We are looking at e to the 2 pi I by 3. These satisfy the equation t squared plus t plus 1, which turns out to be irreducible over q. It's a quadratic polynomial, so its irreducibility just means that there are no roots. And if we take n equals 4, then a little bit of thinking, you may come up with t squared plus 1. So n equals 4 means we're looking at fourth roots of unity, which are 1, I, minus 1 and minus I. Zeta 4 is just I, e to the 2 pi I by 4, and that's just I. And zeta 5, turns out that it's irreducible polynomial is t to the power 4 plus t cubed plus t squared plus t plus 1. And for 6, it turns out that the polynomial is a bit smaller than the earlier cases. It turns out that it is t squared minus t plus 1. So that's a few examples of cyclotomic polynomials. And in the next lecture, we'll try to compute some infinite families of cyclotomic polynomials.